If you want to learn more about MSDP, be sure to check out our Junos Multicast routing course. For full details, just visit juniper.net/courses and search for the course in the keyword search box. This subject also appears in the JNCIP Enterprise exam, so pay close attention. Now let's get to your Learning Byte.
This Learning Byte will be about MSDP, and we will also be giving you a lab example on configuring anycast-RP with MSDP. My name is David Williams, and I'm with Juniper Education Services. MSDP was developed for interdomain multicast solutions. Between domains, we will be using Border Gateway Protocol, or BGP, to exchange routing information for the RPF check. If the unicast and multicast topologies are going to be similar, we will do the RPF check based on the INET 0 table. If there's a case where we have a need for different unicast and multicast topologies, we can use multi-protocol BGP to exchange multicast-specific source address information and do the RPF check on an alternate table called INET.2. The piece that's missing from early interdomain multicast solutions was how the source in domain 1 and the receiver in domain 2 would meet, because, of course, they could communicate with different rendezvous points. The solution to that problem was the Multicast Source Discovery Protocol, or MSDP, which exchanges source information from one rendezvous point to another. The MSDP process enables all RPs with receivers to learn about the sources and thereby allows sources and receivers to connect. The result of the current interdomain multicast solution is that sources and receivers learn about each other, and that the receiver's DR will set up an S-G source tree toward each source for the specific group of receivers. When each internet service provider uses its own RP, it creates a problem when using PIM sparse mode. If the source of AS65001 sends register messages to its RP, that RP has no knowledge of the receivers in AS65002. The RP in AS65002 will know about its local receivers, but it has no way of learning about the source in AS65001. So without any help, the source and receiver will never meet, and traffic will not flow between them. MSDP solves this problem by exchanging source information between rendezvous points in these different domains. When the rendezvous point in AS65001 learns about the source in its local domain by receiving a register message, it sends source active messages to its MSDP peers. In this way, the rendezvous point in AS65002 learns about the source 192.168.100.10 for the group 224.7.7.7, and the source and receiver can connect. Typically, less sources exist in the network than receivers, which is why the solution is to share source information rather than receiver information. MSDP shares multicast source information between RPs so that sources and receivers can meet, even if they are associated with different RPs. In the interdomain model, we'll enable multicast deployments between different service providers. In the intra-domain model, we'll improve RP redundancy through the anycast-RP feature. MSDP is typically configured on PIM sparse mode rendezvous points, although it's possible to configure MSDP on non-rendezvous point routers as well. In the interdomain setup, there might also be domains that never have any sources but still need MSDP to enable transit multicast traffic across their domain. Once a remote source for a group is learned on an RP, The RP establishes a source tree back to the source, assuming the RP has knowledge of the receivers for that group. When the source tree between the source and rendezvous point is established, traffic starts flowing toward the receiver. The first part will go across the source tree between the source and the rendezvous point. The second part will go down the shared tree toward the receiver. Upon arrival of the first multicast data packet on the receiver's DR, the router normally starts signaling its own source tree back to the source, which is exactly the same behavior that you would see in a single PIM sparse mode domain. The MSDP protocol is similar to BGP peering in that it establishes a TCP session between peers. The configuration of MSDP peering sessions is also similar in that the peers must be manually configured. Once the sessions are established, the source active messages can be sent to any MSDP peer. Once the MSDP peers are manually configured, the peer router with the highest IP address remains passive and listens only to connection attempts from the active peer on TCP port 639. MSDP peers can go through different connection states. The active peer will normally go into a connect state. In this state, the active peer is trying to set up the peering session by initiating a TCP three-way handshake. Once the TCP connection is established, the session state becomes established. The SA message is sent by a rendezvous point with MSDP when the rendezvous point becomes aware of a source through the incoming register message. The SA message is sent to all the rendezvous point's MSDP peers. The SA message is sent every 60 seconds until the source stops sending multicast traffic. The receiving MSDP peer stores this information in their SD cache if the message passes the RPF peer check. In Junos, there's a special table for this called inet.4, which is the MSDP SA cache. Any SA message that passes the RPF check is sent to all MSDP peers except the peer where the SA message was received. The example shows multiple service providers, each with their own independent PIM sparse mode domain. Each PIM sparse mode domain has its own rendezvous point, which works for interdomain multicast. To enable interdomain multicast MSDP, sessions are established between the rendezvous points of the different autonomous systems. There is a source, 192.168.100.10, for the group 224.7.7.7 in AS65012, which registers itself at the RP of 192.168.1.1. In AS65014, the receiver is using its own separate RP, and the *G entry shared tree is established between the receiver's DR and the RP. For the source and receiver to meet, the rendezvous point 192.168.1.1 sends SA messages to all its peers, letting them know about the source and group information. The SA message will have information about the originating RP, the source, and the group. The MSDP peers in AS65011 and 65013 perform a peer RPF check on the SA message, and if successful, forwards the message to other MSDP peers. The end result is that the RP in AS65014 learns about the active source 192.168.100.10 for the group 224.7.7.7. The RP in AS65014 on arrival of the SA message checks its local PIM state information to see if any receivers exist for the 224.7.7.7 group learned in the SA message. As a receiver, the DR has set up a *224.7.7.7 shared tree toward the rendezvous point, and the rendezvous point starts sending a PIM join message in the direction of the source. This process establishes a source tree between the rendezvous point in AS65014 and the source in AS65012. Once the source tree is established, native multicast traffic can flow in the direction of the rendezvous point in AS65014. Multicast traffic arriving over the source tree on the rendezvous point in AS65014 is forwarded down the shared tree toward the receiver. Thus, the initial packet uses the source tree to get to the rendezvous point, and the last part of the path is the shared tree from the rendezvous point toward the receiver. Upon arrival of the first packet at the receiver's DR, the DR typically starts its own source tree signaling to set up optimal shortest path tree. Once the shortest path tree is established, native multicast packets flow down the source tree from the source toward the receiver in AS65014. So we're going to do an example configuration based on this slide. As you can see, we have 4 routers with the loopback addresses of each. We have 3 ASs, 65001, 65002, and 65003. So here is the basic MSDP configuration. MSDP neighbors can be configured directly or through peer groups. If mesh group functionality is required, the peers must be configured using peer groups. The source address for the session can be hard-coded using the local address statement. On R4, the default peer command is used to ensure that all SA messages are accepted from this peer. As you can see, the configuration looks very similar to setting up BGP. The show MSDP command shows information about the configured peers, the local address used, the state, the peer group name, and the SA messages received and accepted. To see more details, you can look at the same command, show MSDP peer, specify the peer name, and add detail. You can view the SA cache on the MSDP router by using the show MSDP source active command. The flags field displays whether the SA message was accepted, rejected, or filtered. Another way to look at the SA cache is by looking at the table inet.4 with the show route table inet.4 command. To troubleshoot MSDP, you can enable trace options under the Edit Protocol's MSDP hierarchy. By monitoring the file, you can look at the detailed protocol exchanges. The example on the slide shows an MSDP session being established and an SA message being accepted. You can also use MSDP for anycast-RP configuration. We'll be showing an example lab using anycast-RP with MSDP. A review of the lab diagram will show that we are using, on the left-hand side, the source address of 10.0.101.2 and 10.0.101.3. The receiver on the right-hand side through the vSwitch will be 224.771 and 224.881. The 2 rendezvous points that we'll use in our example on the top left will be VR2 and on the top right, VR6. Okay, so now we will begin our lab on configuring MSDP and anycast-RP. We'll just do a review of the lab topology. Our lab consists of VRs. We have VR2 and VR6 acting as rendezvous points. We have our source, 10.0.101.2 and 10.0.101.3 off of the VR device. And then we have our receivers off of the main instance through the VR device as well. For brevity, we'll assume that PIM has already been configured. And so what our first step will be is to configure the anycast-RP address on our 2 candidate rendezvous points. So we'll go ahead and just check to make sure that that has been configured. So let's do a show interface LO0. Okay. For unit 2, we have 2.1, which is configured as the primary address. Okay, if we don't put the primary statement in there, the 10.1.1.1 address would become the primary, which is what we don't want. And then we have the anycast address of 10.1.1.1. We should have a similar configuration on Unit 6. Okay, so primary address of 6.1, and then we have the anycast address that we're going to use, 10.1.1.1. Okay, so that part should be in place. Let's just check to make sure that we are advertising that 10.1.1 route. So we'll go ahead and do a run show OSPF database router, advertising router, and we'll check from our VR2 device, 172.16.2.1 detail. Okay, and we just want to make sure that here in our router LSA, we see the 10.1.1 being advertised. That looks good. And we'll assume that the same is the case for VR6. Okay. We should also, of course, have a verification of doing a show route to 10.1.1.1 to make sure that it's reachable through all VR devices. Okay, so we'll just do that really quick. Let's do a run show route 10.1.1.1. Okay, and you can see a long list. We should see this address reachable in the main instance and also in all of the VR devices. Okay, so I think we're ready to go. The next thing that we need to do is we need to configure the rendezvous points, and we're going to be doing this statically as what's typically done with anycast. And so the two special cases are going to be VR2 and VR6. So let's go under Edit, Routing Instance, VR2. And let's do a show protocols PIM. Okay, and so for VR2 and VR6, which is our candidate rendezvous points, we should have this configured as RP local. For the other VRs and the main instance, we should have this configured as RP static. Okay, and just to verify, we can do a run show PIM RPS, and we should see 10.1.1.1. Okay, this is for the master instance. For brevity, we won't run this for every instance, but we'll assume that we all agree that 10.1.1.1 will be the anycast rendezvous point address. Okay, so now what we need to do is, if we were to do a PIM join state at this time, we're going to have some problems. And the reason is because we have to connect the two VRs together. So all routers are using 10.1.1.1 as the rendezvous point, but physically the receivers are setting up the shared tree toward VR6, but the source is registering with VR2. Okay, so we need to have the source and receiver be able to meet each other. In order to do this, we will be configuring MSDP. Okay, right now we should actually see some register messages being received on VR2. However, we won't see any sent until we get MSDP running. Okay. So we're in VR2. What we can do is say set protocols MSDP group, and we'll say it's anycast. The peer is 172.16.6.1, and we'll put in a local address statement. So set protocols MSDP group anycast, local address is 172.16.2.1. Okay, and the last step is we want to make sure we don't want to have to worry about any kind of pure RPF rules for the SA messages to get received. So best practice with anycast-RP with MSDP is to configure a mesh group. Okay, the mesh group will allow us to bypass the pure RPF rules. So the last configuration step will be set protocols MSDP group anycast, and we'll say mode mesh group. Okay. So we'll have to do the same for VR6. So we'll repeat the commands really quick. Set protocols, MSDP, group is anycast. The peer this time is the other side, 172.16.2.1. The local address will be us, which will be 172.16.6.1, and the same step, set protocols MSDP, group is anycast, and we'll say mode mesh group. All right. So now we'll go ahead and we'll do some committing. Let's go ahead and commit. Okay. And MSDP inherently, because of the timers and things, might take a little bit to establish, but we'll go ahead and run this and see if we see anything at this point. So let's do a run show MSDP, and the instance is VR2. Aha, so we're looking good. And of course, for VR6, we should see the same thing. We want to see if we have looked at, or if we actually have learned any sources, right? Because remember, MSDP uses the source rendezvous point, originating rendezvous point, plus the source and group as part of the SA message. So one way we can look at the source is we can do a run show MSDP detail instance VR6. Okay, and you notice that we are now getting some SAs, all right? So we have some accepted SA messages. To see these messages, we can do a couple of different ways. We can look in the inet.for table, or we can look at the source active command. So we'll try the command first. Run show MSDP source active, and the instance is VR6. Okay, and here is our rendezvous point originator. Okay, we see the peer, we see the source, and we see the group. The other way we can verify that this is working is we should now be able to do a run show route table, and it will be VR6.inet.for. And this will allow us to also see the entries in the inet.for table. All right? Previously, before we did this step, we would not have any state if we were to run the show pim join. Okay? Now we should be able to do a run show pim join, and we can say extensive, and we should see some state now for our groups that we've defined, 224.771 and 224.881. Okay, so we did a pretty good job. We got everything up and running, and we should, at this point, now see S, G joins, because VR2, which is connected to the source, can now send SA messages toward VR6, which is the rendezvous point with the receivers. We configured MSDP, which results in the receiver's DR learning about the source details and therefore allows the S, G joins to be sent. Now, should we actually be able to verify that multicast traffic is being sent? Well, an easy way to do that is we can just do a run show multicast usage, and that will also give us packet information on this. If we were to have trouble where we didn't see the correct join state or trees being built, we could also configure trace options. There's a trace option flag that you can use for source active or source active detail. Thank you very much for watching this presentation.
Visit the Juniper Education Services website to learn more about courses. view our full range of classroom, online, and e-learning courses. Learning paths, industry segment and technology-specific training paths. Juniper Network's certification program, the ultimate demonstration of your competence. And the training community, from forums to social media. Join the discussion.